All right, thanks so much, Ali. Just a quick show of hands. So how many of you are from EE? And how many are from CS? Okay, it's a good distribution. So thanks again for inviting me to come here today. Excited to talk about the Internet of Moving Things. So fundamentally, in the world that we live in, we have these low-cost sensors coming from the EE part of the world that are now being deployed cheap enough that are pushing data back into the cloud. And that opens up a lot of new possibilities in terms of problems, opportunities, and challenges in how we can reshape urban mobility. So this is really what I've been excited about for the last few years, because earlier, and in fact many of us in this room, a lot of us actually worked on making the web faster and better and more personalized. We built a lot of technologies, a lot of products and services to understand how people move on the web, and built out analytics layers, querying engines, visualizations, products to help people move on the web a lot faster. What we got inspired by a few years back was, how do we take a lot of those same ideas that we had on the web, and how do we apply that to the physical world that we live in? What are the new challenges, new opportunities, especially as the amount of data from this low-cost sensors keeps growing into the future? So in terms of the common simple thread in my talk is going to be about space and time data. So essentially movement data that is coming out of these low-cost sensors and being pushed back into the cloud. So I'll talk about time as well as about space before we get to space and time. So 1,440 minutes every single day is really what we all have. And that's to live and work and play. So one of the key questions for me is, how do we get back some of the time in the physical world that we live in? And that really leads us to how we all move through the physical world in terms of transportation, mobility, and how even goods and services get to us increasingly these days. So over the past few years, my team and I, we've been working on getting billions of movement traces from many different parts of the world, all the way from the connected buses in Sao Paulo, Brazil, that are moving through Sao Paulo, moving millions of commuters every single day, to the connected trains in Singapore, Casablanca, Washington, D.C., and so on, all the way to the vehicles that are moving in our local neighborhoods and picking up more and more movement information and pushing it back to the cloud, where time actually matters a lot. So a lot of what we've been doing is taking the point samples of data that is being collected by these sensors. Essentially, these are all like sensors that are moving, but collecting point observations as they move through space and time. Okay, I'm sure it'll come back on. And essentially, how do you take that data, the dots, and how do you connect the different dots so that you can start asking richer questions, visualize that data, and how do you ask analytics and start predicting more of how people actually move through the physical world? Give me just a second. Let me see if this. OK, maybe that's going to work. So one of the key observations that we had was to connect the different dots. You need to have a very good understanding of the physical substrate of the world. So essentially, when movement data comes to our engine, we mash it up with a model of the physical world, reconstruct paths of commuters, of vehicles, and then start asking rich questions on that data. So before I get to the space-time engine and the engine that we built at Urban Engines, and what we are now going to use in Google, let's spend a few minutes understanding the space part of the equation, location information. So when this is, some of you may remember paper maps from like ages back. So offline, good device, you could use it anywhere. So when I used to come to visit Ali many, many years back from Stanford, we had to open up these physical maps, combine that with bus timetables, the Caltrain timetables, and then merge all that information in our heads to get from A to B. This is how the world has been working for several years. The last the last 10 years or so, Google Maps and many other mapping providers have been looking at how do you digitize that information in a very high fidelity fashion. The roads, the intersections, the traffic signals, the locations, picking up all that information so that you can digitize it and start using it on the web, as well as getting information not only about the world that we all usually move in, but also information about interesting locations around the world, the heights of mountains, as well as the depths of the ocean. Getting high fidelity information of all this is expensive, but is of high value overall, because now we get a true understanding of how the world actually looks. Deconstructing the maps, the spatial part of how the world actually works is really through multiple layers. So you have a notion of a base map, which has the street level information, the angles, the curvatures, the ramps, and so on. Once you have a high fidelity version of that, then you take street level information about the cars that keep driving around picking up information about the different streets, pictures. And then you have the 3D models. In a larger urban environment, having multiple stories with different points of interest is the next level of granularity. And ultimately you have the local substrate, which is the points of interest, the restaurants, the bars, the parks. All that information is at the highest level in terms of local information. Now this information, this is deconstructed. When you construct it back, you can start making that available on your mobile devices, right? Getting from Berkeley to Santa Cruz, getting from Berkeley to your favorite burger place. And also new experiences which actually combines time as well as the amount of money you're spending in getting from point A to point B through tolls and so on and so forth. A quick show of hands, how many of you use Google Maps? Pretty much most of you, that's great. So this information is now available on mobile devices, both online with your connectivity, but also offline as well, which is an important use case for the next billion users, right? So in countries where you actually have less bandwidth, and the latency is too high, having that information on the device itself is a big improvement in those markets. This information, the mapping information, is available not only for the consumers, but also for developers to build rich new classes of applications. So you have rich APIs on iOS and Android on the web, but also HTTP requests that you can start using, whether it's for your places, your directions, your elevations, to start building out new and richer experiences for end consumers and for businesses. So people are building better customer experiences, whether it's your favorite pizza delivery application or finding Pokemon in your local neighborhood, all the way towards optimizing your actual fleets, your vehicles, to leading towards larger strategic decisions about where do I put my next shopping mall? Where do I put my next commercial building, my next residential complexes? When you start having a good understanding of the physical world that you live and move in, a lot of these kinds of questions become much easier to ask and answer. This information is obviously available by developers in your in-car navigation units. And also, here's a fun one: happiest place on the earth. So this is a special collaboration between Disney and Google Maps, where how do you get from Buzz Lightyear's adventure to Splash Mountain? Turns out there's actually an interesting, intricate network of trains and monorails within Disney World. And also, how do you find Goofy, who's just walking close by to you, right? So those are the kinds of applications where you start collecting more sensor information and combining that with mapping data to enable new experiences. So a lot of what we talked about right now is all about the space part of the equation, the spatial information that we are now collecting. And so then now the next question is, what about all the space-time information that is now being collected? So from all the devices that we talked about. So when you start collecting the movement data, which is much more rich than pure spatial data. So movement data coming out of the GPS devices, the RFIDs, the beacons, all these from smartphones, from vehicles, and so on. Not only can you start visualizing the pulse of the city, the mornings, the afternoons, the evenings, but now you can start to ask questions about it in terms of how do you model it, how do you learn from the movement of people, where are the hotspots, when is it happening, why is it happening, and also to start predicting it in terms of looking at the next generation of predictions will be based on this aggregation of spatio-temporal data. So from a computer science perspective, movement is actually a new data type. It's actually a fundamentally new data type. And I'll explain that in a minute. So a lot of the spatio-temporal data that we're now collecting, the rate at which this data is growing, it actually requires a new technology stack to be able to answer questions about this data. Just stepping back in history a little bit, earlier, before the web actually happened, many of us used to use the classic relational database systems to store and process relational data. And then when the web happened, the amount of data was just so large that many of those classic data storage retrieval systems, which is not fast enough, could not handle the real scale of data. And also the problems were different. We didn't care about transactions as much. We cared about different patterns of access. So as part of that, we built new search systems, new MapReduce and Spark-like systems, Dremel, BigQuery, Redshift-like systems, which take a different tack on the kinds of data that is being produced and the kinds of questions you want to ask on that. So these are all completely different kinds of ingestion, indexing, and querying mechanisms that we built for the web world. The next big leap happened in terms of new kinds of data when we actually had the social graph. So as computer scientists and systems people, we wanted to use exactly the same system that we had built for the web world. Pick your MapReduce, pick your Dremel, and apply that to the social graph. Turns out you could go a certain distance, but not very far, because the kinds of questions you wanted to ask on social graphs were much more about the graph structure itself. Who's my friend? Who are my friends of my friends? So a lot of the initial algorithms courses we took as undergrads in terms of how you do graph processing and asking questions on that became much more interesting at a much larger scale, which is why in this phase of data, this kind of data type, Facebook built Tao, Google built Pregel and WebIQ, which were primarily built around how do you ask questions about graph systems at a much larger scale compared to what we were doing in the web world, because the questions were different, the data was different. We have the same problem, or the same opportunity with movement data, because this is spatio-temporal data at its core. So from the billions of smartphones that are pushing data, that are collecting data, this is not true a few years back. Billions of smartphones are pushing data into the cloud. Hundreds of millions of packages that now have sensors that are pushing information back to the cloud. Tens of millions of connected cars, buses, trains. All this is creating this rapid growth in this new type of spatio-temporal data, which is really at its core time, space in terms of lat long and additional attributes. So what we have been working on for the last several years is a system called Warp, which has been primarily built for handling massive amounts of space-time data to ask and answer rich questions. So examples of the kinds of questions we want to answer with spatio-temporal database systems is really the who is creating this traffic? When are the hotspots happening? Where are the hotspots? Why is there a hotspot happening in space in a specific location at a time? Sort of rolling it back. So you roll it back and you want to ask questions like, why did this congestion happen in this location? So you roll it back in space and time and look at what happened before that. And then the what ifs, which is rolling the clock forward and changing the underlying topology and saying if I close this particular road, or if I add an extra set of cars over here, add the fleet over here, add an extra warehouse over here, what happens to my actual movement pattern? So it's essentially questions where you're rolling back in space and time and also rolling forward in space and time. That's really the core of what you'd like to do with such movement data. Examples. So Moscone Center, big place with lots and lots of events. You have your Dreamforce event, you have Google's I/O, you have Apple's WWDC. Events all happen in the same location. But it turns out the patterns of traffic are very different. Even though they start roughly at the same time, the places from which people actually congregate into these locations is actually very different. The better you understand that, the better you actually can model what you want to do to improve that mobility. So as an example, so Apple event, a lot of people come from the Marina district. Google event, the pattern is actually pretty different. So essentially, you can start looking at on a per hotspot basis and roll the clock back and figure out what happened and use that information to do a better job the next time around. This is another interesting one, which is about who. Going from San Francisco to Palo Alto. Many commuters do this every single day. Two choices, 280 and 101. So here, we want to understand how is traffic actually accumulating into 280 and how much is accumulating into 101, and where do people actually come from, and how does it change over the course of the day. So purple is 280 and green is 101. So this is before 8 a.m., this is 8 a.m. to 3 p.m., and this is after 3 p.m. This is obviously 280, but it turns out the folks that are coming into 280 are actually coming from these different parts of the city at a volume. It's sort of like, it's like streams of people starting at a certain location and joining into 280. The patterns are different between 8 and 3 p.m. in terms of where people actually come from and what are the choices they end up making to get towards 101 to 80. So there are interesting zones of uncertainty where depending on when you actually leave, whether 101 versus 280 is better, and the kinds of choices people are making, it's interesting to understand. And here in this more extreme case, after 3 p.m., you can see this purple patch in that area, and up in the top. That's another example where people that are far away from the 280 are actually starting in that region and eventually ending up in 280, because that's the pattern that you actually have with 101, right? So this is an example of a kind of a question where you're looking at traffic patterns and understanding what actually happened before. Question?
The question about this data, is this an estimation or is it actual data? Because if it's a real data, how do you actually know that people are coming from that location and they are going to 280 versus 101?
Yeah, so the question was around, is this actual data or is this simulated data? So in this picture, I'm actually showing simulated data because we take user data very, privacy around user data very seriously. But there are similar kinds of things we can do with real data as well. So when you have real data, which is what Google and Apple and other companies actually have, you can actually run these models at a large scale. So the next question is around an example of a what-if scenario. So we had Super Bowl 50 last year in Santa Clara, but it turned out that there was a lot of events in the city. That there was concerts, there were special parties that were happening in the city. So one of the questions you want to understand is before, clearly after the event, you know what exactly happened. But one of the things you want to know before the event actually happens is if my commuter demand is going to be 5% higher from Fremont, or 10% higher from Santa Clara, or 20% higher from Berkeley, what is my patterns actually look like? Where are my hotspots going to be? And how does that propagate backwards so that I can build more capacity on those specific kinds of routes. So building out these large-scale emulations to understand what is the impact going to be on the commuters and on the vehicles is another important property of these space-time engines. So here you can see that there's the reds. This is like a normal. This is normal demand between 2 and 3 p.m. And this is different demand with like additional people coming in, 20% additional capacity of people coming in because of these parties. So you can get to see the hotspots and predict and improve your capacity. Let me pause for a minute to see if there are any other questions before I switch to some of the underlying technology. Any questions? Yeah.
The previous slide, how did you set the time boundaries? For example, why is 8 a.m., why is 3 p.m., why not expected boundaries?
So the question is, why did we set specific time boundaries? I mean, I had to pick one picture to show, and 8 a.m. and 8 a.m. to 3 p.m. seemed like a reasonable one to pick. But in general, with an engine, you should be able to change those boundaries and say, let me look at 8:15, or let's have a boundary between the nuance boundaries even within those time periods. With an engine, with a space-time engine like what I'll talk about next, you actually can ask these kinds of ad hoc questions and see where the boundaries are. But for this talk, I picked specific times. Yeah.
So I have two questions. One is, you have the data of people who are using your app, Google Maps or something like this. The people who have iPhones and using the Apple Maps don't show up on this. So you have an incomplete set of data. Uber has another set of data. Verizon has another set of data. But if you want to do integrated transportation planning, you'd really like to know where everybody is moving. Is there any prospect of that happening? And the related question is, the people who actually have to make decisions about transportation policy are not Google. I mean, you run some buses, but otherwise you're not in the transportation business. It's San Francisco Muni, BART, Caltrain, all these other sorts of people. But they don't have this data. You have the data, or Verizon or Apple or somebody else has the data. So two questions. What's being done about data integration, and what's the prospect of the transportation planning agencies getting at this data?
So two questions. One is around the fact that people use different operating systems. And so we have a slice of some of this data, not all of it. Second question is around how can we make more of this data actually available to external sources like the planning agencies. So the first part, in terms of, you're absolutely right, this is a sample of the data that Google would have. So in this case, I'm actually showing what we were doing at Urban Engines. So our next phase is actually about looking at Google's data as the next step. We just got acquired like a month back, so we haven't done the integration yet. In terms of the coalescing of data, this actually is going to be an interesting problem from a privacy standpoint, and this is an ongoing conversation that will probably take some time to resolve. But ideally, what we should be able to do to answer the second question is, the raw data itself is such a massive scale. What we are trying to do is offer applications on top of this data so people can have a better sense of what the data actually looks like. Because this is massive, right? The rate at which the sensor is actually producing data is huge, and just keeps growing over time. And so we've actually, at Urban Engines, we actually have been working with planning agencies that are doing short-term operational improvements to buses and trains, and also for longer-term urban planning opportunities, where they're looking at using movement data as a way of improving, like, where should I put my next set of bus stops? Where should I put my next office complexes? So I think the way in which they consume data is actually through interesting applications. That's what we'll be looking at, how to offer some of those.
So you're talking on the next slide about some amount of planning if traffic from Fremont increases, what happens? To what extent do you look at the interaction between traffic and getting information about traffic? So someone who looks at it and says, oh, traffic's 2 hours now as a result of the Super Bowl.
is a question about how do we take this large-scale traffic data and how do we make that available to end consumers?
My question is, how does end consumers having access to that traffic data then affect your predictions of what that traffic data is going to look like?
Great question. I think these are some of the kinds of questions that we will be answering in the next few years, because it's only in the recent past that we've been getting this massive upswing in data. Earlier, it was much more static spatial data, and then you were layering on like real-time traffic on top of it. But now the next question is, now that we know how fast this data is growing, how do we take that information and run these what-if predictions on that data to see what is the potential sloshing that is going to happen in terms of how people may move from one set of roads to another set of roads? Those are the kinds of models we actually should be able to work on next.
Some people commute into San Francisco via BART, which is underground by the time they hit San Francisco. So there are no GPS signals. In most of BART, there's actually no telecommunications except possibly at the stations. Are you trying to address this at all?
So at Urban Engines, when we built this engine, we were actually working directly with people like BART, with the data that they were collecting, with the GPS devices they had, the commuter smart card information they had, like the Clipper card and so on. So we were working with those folks directly because they have tons of interesting data as well. That's true for a lot of the smart city facing work that we were doing in the last several years. So working with Singapore's buses and trains. They had all their commuter smart card data that used to come into our engine. So I think there's two sort of ways in which this would be interesting, right? One is you already get from people's movement with GPS and the mobile operating systems, you get a sense of the rough density of people. And then when you supplement that with high quality information from these end users that are producing the data, the end departments that are producing this data, I think that merger would be pretty interesting to look at. So at this point, we're not working with them directly, but that's an opportunity in terms of having higher quality data with much more sort of dense data, but that's more global, but it's sampled in some way. Yeah?
I was wondering, how did you guys make this simulation? Or is this simulation or real-time data?
Yeah, it actually is actually emulations. So when you actually have like origin destination information, then you actually can start looking at the choices that people actually have in terms of whether it's a bus or a train or whatever, and then you run different models. It's very similar to NS2 or NS3 in terms of how network simulators worked, but now being applied to the physical world. So let me switch to a few of of how the tech actually works, and then I can answer more questions. So roughly what happens is, and this may answer some of your questions as well, is we essentially get location data, from these GPS units, beacons, RFIDs, from vehicles, from infrastructure, from the cities themselves. We take that data and then we have some kind of because of streaming data, which is coming in at a rapid rate, use some kind of a cloud pub sub model to be able to ingest that data, canonicalize it, and then push it into an engine like BigQuery or into Warp, which is the engine that we've actually been working with. So these systems handle streaming and batching in terms of getting that data in, streaming it, batching it, and pushing it to make it available for querying and for visualization. So that's a very high-level picture of the data flow. Now looking at the actual query flow, so it's a very it's a typical sharding and replica kind of a model that many of you are probably familiar with. Each of the shards are responsible, each of the machines are responsible for some slice of space and time data. So locations around the Bay Area, and then the user level data at in that region. So essentially we have these space-time shards which are cut up and offered on these machines, and they have replicas which actually can serve as more read-write traffic. And then the machines themselves, the actual shards, what they do is they do a few different things. The classic SQL style queries in terms of being able to group, aggregate, filter, and so on. But in addition, what this engine actually does, it actually does geo operations. Geo operations such as data coming in, like a noisy GPS trace, how do you snap it to a road segment? You need to have that spatial information to be able to do that. So geo operations, that are all the classic geometric and geographical operations is what this engine actually does. Routing, in terms of being able to modify the underlying network. Routing in terms of how to get from A to B in the fastest way possible, but also if you change the underlying topology, like if you take out a road, or add an extra lane, or add an extra bus, what happens to the actual flow of people. So this engine is really cutting up the entire world into smaller pieces, and then data comes in, gets mashed up, and is stored as a querying engine. When you want to do like what if simulations, then you change the underlying topology, rerun all the traffic data, and then store it back into this engine. And you can again query and process against that. So that's roughly how the engine itself actually works in terms of mashing up geo operations and doing emulations. So this is a bit more lower level in terms of how this system actually works. This is the life of a pipeline. So life of a pipeline is really the mechanism through which you would ask these questions and run these simulations. To work at scale, we have different set of servers which use local storage, working off of some permanent storage like S3 and GCS. At the top, you have something like a schema manager. So in relation systems, we had schema managers, right? So similar to that, we have a structure manager which has the structure of the actual data. Then you have a catalog manager, which is conceptually where the actual indices are, where the locations are. So breaking up what the data is and where the data is actually being stored. And that's really what these things actually keep track of. When a query comes in, this is really the kind of an ad hoc query that you can run to ask questions across the space-time engine. I'm not going to go into the details of the actual language syntax, but the thing it's trying to do here is, it's from all the points of interest, from POIs, it's trying to find, it's finding all the restaurants in California, and then aggregating it, grouping it by locality, so like specific regions, and then counting it all up. That's really what a pipeline looks like. The reason why we chose a pipeline-oriented language is so we actually can go away from the SQL style world and be able to ask these richer spatio-temporal queries, and also be able to split this efficiently across many different servers. So the result of this would look something like Mission Street, the number of restaurants, there is 25 restaurants. Palo Alto, there's 230 restaurants. That's really what this pipeline would do. So the pipeline comes into these machines, and then they get shipped around to the other machines against service, if they have the right kind of space-time shards, and would get back the results back into this aggregate. And that's really the model through which we can run large-scale queries that are ad hoc, large-scale emulations with a bank of servers that can work with this data. So that's a pretty high-level summary of how the backend actually works. But really, the goal of what we've been trying to do is, from all this movement data, ingest it at a very fast pace, and understand this from these point observations, how to connect the different dots, and from that ask these rich questions, but what is truly happening in every single minute and mile. So that's what we've been doing, and love to answer more questions. Thank you. Yeah.
So you mentioned before that movement is a new data type.
Yep.
Could you explain a little bit more how you went about designing the query language? You mentioned SQL is too strict. So how did you design around the semantics, and was it stable? Did you have to change it? How does that affect how your system design works?
Sure. So this is yep. Yeah. So the observation was, we were inspired by pretty much what happened on the web and in social graphs earlier, right? The kinds of questions you want to ask on this are the questions I listed out data, which is the when and the what and the why, right? So the engine we built is really addressed to answer those kinds of questions, and to handle the large scale was the other dimension of what we were trying to accomplish with this, which is why we're calling this as a new data type. And the spatial-temporal data that you want to have with such large data is really what we're trying to focus on. So that is the motivation behind why we wanted to build the system. In terms of the actual language, few things. Even in the evolution from relational database systems to MapReduce, right? MapReduce had a bit more power in terms of dealing with large-scale data and doing certain kinds of filtering and aggregation operations. That was interesting for a while, but it could not handle any kind of social graph kinds of questions. It doesn't really handle any kind of spatio-temporal kinds of questions, right? So a lot of the primitives we used are fundamentally chain MapReduces along with spatial, temporal filters and aggregates, where the pipeline language helps us localize the computation to these space-time shards. So we had a level of control with the language plus how we laid out the actual data to be able to answer these richer questions.
Yeah, I had a question. The examples you gave, the points of interest, like briefly, you said, let's talk about Mission Street and I guess it was Palo Alto, but whatever. So those 2 points of interest, those seem like very different scales. So I guess my question is, when you talk about sharding across space and time slices like chunks, when you're talking about spatial slices, how do you decide? How do you know ahead of time that this little chunk, this is Market Street or something, it's going to have a lot of information, and this chunk is more rural area, and so we can have one server cover a whole lot more room or something, and then whereas if you were sort of just doing it by square miles, you'd have sort of like different concentrations of interesting data versus space or whatever, since it's not like actually spread out evenly or anything. So I was just wondering if you had some, insight about that.
So, this is really getting back to like what is a zoom level, and what is the amount of information density in a specific region, right? So, a lot of what we've done is actually assuming, just looking at the coverage and keeping the actual hashing pretty simple. But I think there's a huge set of opportunities around, like understanding that the filtering selectivity estimates in some way, and building that into an engine. We haven't done any of that yet, but that's one of the things we'll probably be looking at next.
Okay.
But yeah, it's a good point. This is like one of those classic selectivity estimates. How do you index it, and how do you, what are the popular spots, what are the popular data items? All the usual database techniques that have been invented over the last several years will apply in this case. We haven't done any of that yet. Yeah.
So when I think about this kind of traces, these point traces that you're collecting from lots of places, it seems that 5 days ago where some phone was as a point of information, right? That's something that came into the system, right? This little location that
that its value is, as an individual piece of information has decayed away. Like no one's ever going to query where that phone was at that particular time anymore. But some aggregate thing that was a part of, some other information might have some longer lasting utility. How is that something that sort of you think needs to be represented, or you just plan on remembering all this stuff forever?
Right. So it's so it sounds like the question is from these unique data points, there's some delay, there's some decay that happens over time. Is keeping that raw data actually useful, or is keeping some semantics of what actually happened on that specific road segment actually more useful? So,
What's done?
sorry?
And what's done? Like you described the system.
Yeah.
How do you-
So we do keep the raw data, but also we do decay it over time. But essentially, we do keep summaries, so that you get to know what is happening in specific road segments and speeds and so on and so forth. Right? What is the value? So far, the aggregates beyond a certain point are actually pretty darn good. But even in terms of like coalescing all that information today, now, yesterday, you still need an engine to be able to process that at a massive scale. So the individual point observations will be semantically compressed, and that's pretty useful. The actual raw observations may not be as useful over time.
So the most important question, 8 a.m., Berkeley to Stanford, what's the best way to go?
I should go ask my engine. I mean, that's an interesting question, because so far we've talked about primarily single modes of travel, right? When you start having mixed mode of traveling, multimodal, then actually the questions become even more interesting, right? So for example, does it make sense for you to bike or walk to your BART station, take BART to Caltrain across to Stanford, and then take an Uber in the last mile? That may be the fastest way. But and also it's a matter of how much time do you want to spend versus how much money you want to spend, right? What we've noticed is that every single day in a city is actually, the stories are different. It's raining. Is there an event going on around the AT&T park? Is some road closed? It's sort of like the butterfly effect in some way. So every day is pretty different. So stories are different. So I think the best value for the consumers is knowing real time what is truly happening and what is the best sort of combination of paths through which I can get from A to B. Market Street to Moscone Center, what is the fastest way? Is it walking, or is it taking an Uber? Or especially with one-way streets, it gets to be even more interesting as well, right? So I think that's part of the opportunity in some way. The combination of all these discrete data sources to be able to help the consumer, and also help once you understand the commuter demand, helping the planning agencies to help them reshape how urban infrastructure actually works. That's why this area is actually fascinating. Like pretty much all the problems that we worked on the web and digital networks is coming back in terms of new solutions, new analytics, new products in the real world.
So, what sorts of spatio-temporal queries do you see, like, users asking? I mean, like the most basic case, like I'm familiar with a lot of spatio-temporal data, like the use case ended up just going down to lat-long bounding box and, like time bounding box or something. But do you see something like, I guess, trajectories or something, and then, moving, like, if this trajectory is similar to that trajectory, give me some space, some ball of trajectories in, some trajectory space metric or something. Like, is that something that you see, like people asking these sorts of these systems?
Yeah, exactly. It's the richer kinds of queries. Earlier, I think part of the challenge we had with spatio-temporal databases was is more geometric in a way, because you had a polygon, or you had a like a circle or whatever, right? And you work with that, right? A lot of the queries that we are seeing that are interesting is actually of geographic types. What are near POIs? What is happening on Fifth Avenue in Manhattan? What is happening close to the stores around that? So going from geometry to geographic data, from points to paths, those are the kinds of questions that we are addressing.
Can I,
Yeah?
So you just said, like what's happening around Fifth Avenue. What have you been able to define the word around? Like what's around? Like what's the radius or something?
Excellent question. So this actually, as the crow flies is one way of looking at it. That's the geometric way of looking at it. But in terms of like, if you want to look at the Manhattan distance in how you get from point A to point B, that changes the kinds of questions you would be asking, right? So how far is it around is subject to like a 5-minute walk, or a 3-minute Uber ride, or a 8-minute car ride, right? Those kinds of questions become richer. So paths matter a lot in this case. Again, right, a lot of what we used to do earlier was geometric because we didn't have the speed, the capacity to do those kinds of interesting questions. But now we can. Especially now that you have the path level information, you can ask richer questions. So prediction, learning, modeling, and so on.
Any more questions?
Well, thank you guys. Thanks so much for coming.